Did you know that the Statue of Liberty used to be shiny copper? So did the roof of the Parliament buildings. Why did they turn so green? This chapter is on the reduction and oxidation of metals. And this original first section is on chemicals and chemical change and compounds. So we're going to talk about some terminology, including some ancient terminology. So one of them is metallurgy, which is the heating and hammering of copper into shapes. And archaeological studies show us that ancient civilizations were not only using metals, but they learned how to manipulate it. So metallurgy is a really old technology. So we analyzed copper artifacts. Archaeologists can use the chemical analysis in the different copper to track trade routes and locations of ancient industry, depending on where the copper was mined to where those copper artifacts were found. Tarnishing is the color change and loss of luster associated with a metal over time. So silver tends to turn black over time, while copper tends to turn green. So the Statue of Liberty was once bright and shiny. The Parliament roofs in Ottawa are being refurbished from their tarnished copper green to their bright shiny copper metal look again. Silver tarnishes, and this is a chemical reaction between the metal and the molecules in the air. So we're going to balance this reaction between pure silver and hydrogen sulfide and oxygen in the air. So when we balance equations, we want to often start with our compounds. So here we have 2 silver ions. Let me go back. We have 2 silver atoms and we have 1 silver atom on this side. So that's going to have to be balanced. Currently sulfur is balanced, but we have 2 oxygen there and 1 oxygen here. So that's going to be imbalanced. So when we look and go through, we put a 2 in front of the hydrogen to the water to balance the oxygen. We can then balance everything else out. So we have 1 oxygen, 2 waters. We'll now have 4 hydrogens on the product side, so 4 hydrogens on the reactant side, 2 sulfurs on our reactant, 2 sulfurs on our product. So we have 4 silvers on our product side, so we need to make 4 silvers on our reactant side. So we're going to make a Lewis dot diagram for the entire reaction. We have our 4 silvers plus our hydrogen sulfides and our oxygen, giving us silver sulfide and water. So in the last slide, the number of molecules we had to draw corresponding with the number of coefficients in the balanced equation. So we had 4 silver molecules drawn, while we had 4 as a coefficient on silver, 2 hydrogen sulfides and in our balanced equation and 2 molecules of hydrogen sulfide. So when an equation is balanced, we can use the coefficients to compare the ratios of one compound to another. So in this chemical equation, we'll have 2 molecules of water, 1 molecule of oxygen, 4 molecules of silver. And we can do this to calculate masses of reactants and products in a compound, in a reaction. So remembering from Science 10, the rules for balancing an equation means we must always have the same number of atoms on both sides, the reactants and products of an equation. So to determine the correct first thing, we want to determine the correct chemical formula for all the reactants and products. We want to check for any diatomic molecules like hydroxide or sulfide, check for polyatomic oxygens, check for polyatomic ions, and indicate the correct state of the compounds. Are they solid, liquid, gaseous, or aqueous? First, we're going to balance the metals, then the nonmetals, balance all the hydrogens, and lastly, balance the oxygen. Double check with a recount. If every coefficient will reduce, so if everything's an even number, we can rewrite the whole equation using the simplest ratio of coefficients. So we want to balance this equation by adding a coefficient to the front of the chemical formula. Coefficients must be whole numbers, so we're not doing any 2.5s. We can't change any of the subscripts in the chemical formula because then our elements and compounds are going to be unbalanced. We don't want to place coefficients between atoms or ions in a formula, and the number of polyatomic ions, like sulfate, must be the same on both sides of the equation. So we don't want to break up those polyatomic ions. So balancing some of these chemical chemical equations, we're going to start with metals first. So here we have 1 potassium and 1 potassium, 2 chlorine and 2 chlorine. So I have to put a 2 coefficient here. Okay, now I have 2 potassium, so I'm going to have to add a 2 to the potassium on this side. Okay, now I have 2 potassium, 2 iodide, 2 chloride. Oh, the 2 here went away. 2 potassium, 2 chloride, 2 iodide. So my equation is balanced. Okay, in my second equation, my aluminums. Now I have 2 aluminums on my product, so I need to have 2 aluminums on my reactants. Looking at my polyatomics, I have 3 sulfates, so I need to make 3 sulfates on my reactants. Well, now I have 3 times 2, so 6 hydrogens. So again, 2. I want to put a 3 there to make 6 hydrogens. Now, none of these can be reduced because we have a 2, a 3, a 1, and a 3. So wherever there's a blank, there's just a 1. So we don't write it in. That would be redundant. Okay. Now, lastly, we're going to look at the third equation. So if I look at cobalt, I have 1 and 1, zinc, 1 and 1. So now when I look at my nitrate, I have 2 on one side and 3 on the other. So my lowest common denominator is going to be 6. So I'm going to put 3 as a coefficient for that compound, and a 2 as a coefficient for that compound. So now I have 6 nitrates and 6 nitrates. Well, now I have 2 cobalts and 3 zincs to balance up my equation through my recounting. So the mole ratio is the ratio of coefficients in a balanced chemical reaction. So the amount of moles before a reaction is the same as the amount of moles after the reaction. It doesn't tell us the exact proportions, but it gives us the amounts. So a mole ratio of 3 to 1 means we might have a moles of the 3 moles of the wanted element for every 1 mole of the given element. And if we know the moles of the given element, we can use the mole ratio to calculate the number of moles that are required. So we want to write a balanced equation for the reaction. Under the equation, we want to write the numbers of the moles given and the number required under the required substances. So a question might say, well, how much silver sulfide do we need to determine, or how much silver do we need to make this much silver sulfide? We're going to find the mole ratio by placing the coefficient for the required substance over the coefficient for the given substance. We multiply the number of moles by the mole ratio to find the number of moles wanted. So, determine the amount of silver required to make 0.876 moles of silver sulfide based on the reaction. So we write the balanced chemical equation for the formula. Then, under the equation, write the number of moles given and the number of moles required. So in our question, we were given that we had 0.876 moles of silver sulfide. So that's going to be on our product side, and here is that moles. Now we want to find the number of moles of silver required to make that happen. So find the mole ratio by putting the coefficient for the required substance over the coefficient for the given. So this is the coefficient that balances our equation. So we have 4 moles of the required substance for every 2 moles of the given substance. So before we go to this step, we can keep our 4 over 2. So for some of you guys who like cross multiplying and dividing, 4 over 2 is equal to x over 0.876. So that's what we're going to be rearranging. So now we're going to take 4 times 0.876 divided by 2. And then it gives us our answer of 1.75 moles. So I just wanted you to see that in that cross multiplying and dividing. So here was our required, here was our given, the x is what was required, and that 0.876 was what was given. So for our next practice problem, we're going to look at how many moles of oxygen are required to burn 5 moles of propane. Now we're given the balanced equation, and so 1 mole of propane is burned for each 5 moles of oxygen that are present. And so we are also given, our moles given is 5. And so we need to find our moles required. So we're going to take our mole ratio, and again, remembering that there's a 1 here, and go 5 moles of propane. And then we're going to multiply this by 5/1. And this gives us a total of 25 moles of oxygen required to burn 5 moles of propane. I hope you enjoyed today's lesson. See you next time.
If you enjoyed this video, check out our website online.plrd.ab.ca and visit us on Facebook, Prairieland Online Academy. You can find out all that's going on with Prairieland Online Academy.